Our next speaker is Professor Akane Sano. She is an assistant professor in Rice University and a director of computational well-being group there. She works in ubiquitous computing, computational well-being, and among several best paper awards, she has recently bagged the NSF Career Award. A warm welcome to you, Akane, and the floor is all yours.
Thank you very much. Can you hear me?
Yes.
Let me share my screen. Thank you very much for having me today. My name is Akane Sano. I'm located in US, United States, Houston. And today I'm going to talk about multimodal sensor-based machine learning for mental health. And I found the previous talks very interesting, and we have some overlap. And I was very excited to hear that as well. And so, as everyone knows that, we have a lot of devices around us to allow us to capture like moment-to-moment data about us. And so my talk today is mostly how can we leverage this kind of data for personalized medicine, especially in mental health. So then, as you can see here, there are so many different devices on the market. Like that can be wearable, mobile phones, some like eyeglasses or smart glasses. And those data, again, can give us 24/7, like multimodal time series data. So how can we take advantage of these data for improving health and well-being? So we have like digital phenotyping. So this is a term defined as like moment by moment quantification of individual the human phenotype in situ using the data from personal devices. So these data can be very promising because previously, if patient or some people have some issues about health, then they go to see a doctor in a hospital, and then traditionally, for example, electronic health record and also some other patient reported outcomes has been used for diagnosis or monitoring health conditions. But we also have newer data set from the smartphone, wearables, and these can be used for understand this patient without going to hospital like 24/7. So we can aggregate this information together to help medical doctors or health providers to make some decisions, or also can help caregivers to provide some cares or suggestion to patient. So this is a slide I always show in my talk, and so this graph is showing how our health and well-being, for let's think about mental health in this case, can be changing over time if we have a lot of stress. So most of us might be very positive at the very beginning. However, with a lot of stressors from the daily life, some people can stay resilient. However, unfortunately, that's not everyone. And some other people, their well-being or health condition can be going down. And it might be too late to notice if they are reached very like negative condition to come back. So what we want to do here is we want to forecast how people will be doing in the future. And we want to provide some interventions, personalized intervention to prevent them going to negative state. So I direct computational well-being group at Rice University. And so our mission is to design computational methods and tools for measuring and improving health and well-being. And we are very interested in understanding human in daily life setting, so outside a hospital, outside laboratory. So we have three main research topics. So one is measuring people in daily life setting. And the second is how can we leverage that data from daily life setting uh, to robustly infer people's health condition or other human outcomes. And we are also designing intervention and support systems for health and well-being. Then our studies, we run a lot of human studies, and our studies include observational or intervention field studies. And we study both like non-patient population as well as patient. So non-patient population include college student, office workers, shift workers, also caregivers. And we also study patient with mental health disorders. Also, the technology we are developing is also definitely works for like more generalized, personalized medicine. So we are also working on like cancer and epilepsy domain as well. And so we measure a lot of things in our study. So this is multimodal. So some of the data come from like wearable mobile phone. We also have like surveys, questionnaires. We have like clinical assessment, EHR, blood, MRI for some studies. Then during COVID, we were also doing some studies remotely. Then this COVID-19 also allowed us to think about how can we like measure, understand the people using this kind of technologies remotely. So we are running currently two studies. One is for dementia spousal caregivers to understand their social distancing and physical mental health. We also study just regular workers to understand their productivity under this COVID situation. And what we are hoping to do is we are hoping to develop this kind of personalized feedback system combined by combining like sensing and inference and also intervention modules. And we want to provide like personalized feedback to each individual user. And just give you a quick overview of what kind of things we are sensing. We use wearable and mobile sensors in most of the studies, and so that can capture, for example, how we move, physical activity, how we travel, mobility patterns, also social interaction from phone call, SMS logs. But we don't record their conversations or actual SMS messages. We also capture physiological signals like heart rate, skin conductance, respiration. And for some studies, we also combine them with computer usage. Then recent studies, we are also interested in using contactless sensors as well. So that includes some cameras and radar sensors. And we can monitor like facial expressions or some like physiological signals without asking them to wear the sensors on their body. Then using the data from these sensor modules, what we are trying to do is we hope to like, continuously measure and predict people's like, stress or mood or mental health construct. We are also interested in understanding people's like, performance or measuring circadian rhythm, sleep, or clinical event for clinical studies. Then for intervention, we have been trying in different interventions, but these interventions has to be like personalized and also provided to users at a good timing, because if people are stressed and people are doing something else, and it might not be effective to just tell them ask them to do something. And so our intervention has to be micro intervention. So that is something very small that can be done very easily, quickly, in a few minutes. And for some studies, we use some mindfulness-based suggestions. Then for other studies, we have also tested some like low effort interventions. That means we can, for example, provide some light, or we can change the intensity of screen on our computer, or we can provide white noise for controlling like heart rate and breathing rate. Of course, we get users' consent to do this, but this kind of like passive stimuli, multimodal stimuli, can be also helpful to regulate their physiological conditions. Then for these interventions, so we need to kind of design when and which intervention should be provided to users based on their context, history, profile, preference, etc. Then when we design this kind of system, we have a lot of challenges. And so a lot of challenges we have. And the first challenge is, so these data are coming from their daily life settings. So we have a lot of noise and missing data. So sometimes some sensors might not be working, or might have a lot of artifact. And then we need to extract meaningful information from this high dimensional time series data. Then we also need to think about how to integrate this multimodal data. So sometimes, the sampling rate are different. Then this is also applies. This was also mentioned in a previous talk, but we have a lot of individual differences. And how can we adapt our models to each individual? And also compared to the computer vision, speech, or natural language processing research, it is much harder to collect like bigger data from this kind of like physiological or behavioral data from participant or patient. So today I'm going to talk about what kind of technology or tools we have been developing to overcome this kind of challenges. Then whenever we run our human studies, it is very important to collect high quality of data. Then also we want to run our studies effectively, because our data collection can be long term, like 30 days to like 1 month, 3 months, like 6 months. So it might be too late to notice that, the data quality is too poor at the end of the study. So during the study, we need to continuously validate our data. So we need to check our sensor data are okay, phone data are coming in, also whether participants are filling out surveys. And this data validation has to be done automatically. And if something happens, then the system will let us, like study investigators, know, and also participants know that we have to do something. For example, we need to replace sensors, or we need to kind of engage our participant to answer more surveys, etc. Then also, as I said, our data is coming from daily life setting. So some of the physiological data can be very noisy, especially. Then, so we need to identify which part of the data are noisy, and which part of the data are clean. Then in this case, we made some machine learning classifier that automatically identify the noisy epochs versus clean epochs for skin conductance, which is a micro sweat we can measure on our skin, and it is an index of our sympathetic nervous activity. So we made this kind of binary classification model to detect artifact based on the data we collected previously. Then using this classifier, we can identify this kind of like red portion might be noisy. So we can use this information for further analysis. Then after we collect data, we have to think about how to analyze, how to model those data. Then we can extract a lot of features manually based on domain knowledge, or some but also we can use some deep learning model to automatically extract some features. Then if we manually engineer features, then we can extract so many features. So this is an example of our multimodal data we collected from college students from wearable sensors, mobile phone surveys. Then we could extract this kind of so many features. Then, but other than that, since we are collecting this kind of raw time series, physiological and behavioral data, and we might be able to also apply like deep learning method to automatically extract some meaningful information. So this is the work we did last year or so. So we developed this kind of long short-term memory network-based denoising autoencoder to extract some automatic representation from multimodal sensor signals. So this framework is, so we fed 1 day of 24 hours of sensor signals, because in this study, we wanted to predict like daily mood or daily stress levels. So our input data can be super long. So to reduce some parameters in neural network, we use some locally connected layers for so every 3-hour data. And then we aggregated those like 3-hour chunk of data for LSTM neural network. Then we use denoising autoencoder to reconstruct the data so that we can also extract representation from the input. Then we found out this kind of automatically extracted features are useful, and we can reduce the dimension of input data greatly. And those automatically extracted features are still can be used for predicting human construct accurately. Then we also wanted to understand what kind of information were learned in this framework, because otherwise it is a pretty black box. And so we decided to do some correlation analysis between these automatically extracted features and handcrafted features. So these figures shows us some correlation between auto features versus handcrafted features for skin conductance and skin temperature and acceleration. And we can see some of the meaningful features. For example, skin conductance, we found some mean amplitude, number of peaks. These are important. And so we kind of understood that this framework is still learning something we can interpret and make sense based on prior knowledge. Then from now on, I will also talk about what kind of like mental health prediction and decision support system. And first of all, I want to introduce some of the data we collected in the previous studies. So this is the data we collected from college students for 30 days. And you can see self-reported happiness, calmness, alertness, energy, and health levels reported using the 0 to 100 scale every morning and every evening from day 1 to day 30. So this is on the left side, you see the grand average from about 50 participants. Then on the right side, this is another example from only one participant who unfortunately went to hospital and hospitalized for mental health issues. And you can see a lot of difference between these two panels. Then if we compute like average mood, self-reported mood over 30 days, and mood variability as standard variation on the y-axis, we found out we can find some like 3 clusters in this data set. Then we can also fit this kind of line. Then we found that people with sad average mood show higher variance in their mood. And we are also interested in how sleep influence our mood. And so we compared regular sleepers versus irregular sleepers. And we are very interested in understanding people's like rhythm, also routines, because we know that the sleep duration is important, but also recently sleep regularity is also important for health. Then as we can see here on the left side, so this is the how people sleep from day 1 to day 30-ish. So this black boxes, these black boxes are when people in the bed. So on the left side, these are regular sleepers. So you can see these people have almost the same bedtime and wake up time. However, on the right side, you see irregular sleepers' sleep patterns. So very irregular sleep patterns. So we analyze how this sleep regularity affect self-reported well-being by controlling for their gender, sleep duration, and stress score at the beginning of the study to estimate causal effect. And what we found here is we found irregular sleepers shows much lower mental health scores, also lower happiness, alertness, energy levels. Then moving on to like mental health prediction models. So we are very interested in whether we can predict people's mental health or mood, stress condition in the future using the data up to today. So we have been developing different kind of models. And then one of the biggest challenges we have is individual differences. Because as we know, everyone is different. So what makes one person happy or stressed might be very, very different from what makes other people happy or stressed. So we need to consider the kind of individual differences in our models. Then how can we do that? Then, as the previous speaker also mentioned, we are using this kind of multitask learning model. So this multitask learning model, this allows us to train a model tuned for like each participant or group of participant patient, while still learning the model for the rest of the participant. So this is multitask. So this is multiple task learning. So we can learn the multiple tasks together on the model. Then we have been trying different personalization. So ideally, we want to make a totally personalized model for each individual, but we need some data. We need, of course, more data is better. Then that means we want to cluster some people based on their profiles, their gender or their personality type, their profiles to find the group of people who have a similar characteristics. And this kind of cluster-based learning is helpful, especially to adapt new participant to the model. And we learned that this kind of multitask learning-based personalized model is helpful. It can improve the performance much better than non-personalized model. But we also tried different personalization method. And recently we also found this kind of transfer learning can be also useful. So we can pre-train some models with some participant of data, then we can fine-tune some layers of neural network for new participants' data. then this transfer learning is helpful, then especially effective with even like small amount of newer data coming in. Then I also want to introduce some of our research effort about like clinical, like mental health population. So we are also doing like digital phenotyping plus AI research in schizophrenia and also depressions and others as well. And in this project, we have a data collected from patients with schizophrenia, their smartphone. So we can capture many different information about their phone usage and mobility and behavior. And we have developed different models using some statistical features, etc. But we also wanted to develop more like interpretable models. And then we are also interested in understanding how people's routine or rhythm affect these patient symptoms or relapse or social functioning. Then in order to develop more interpretable models, so neural network can be powerful, but it is a nonlinear model, and it is difficult to interpret how the input interact with output. So we decided to go with like a linear model. Then, but this model is still using multitask learning, so multitask linear regression models. And so this was helpful to personalize our model. Then, for example, this is some results from our schizophrenia self-reported symptom prediction. So these blue lines are predicted values, and these orange lines are ground truth. So we predicted, for example, like their self-reported scores about hopeful, harm, seeing things. And this linear model are helpful because we can also understand the subtypes of patient. So different coefficient in a linear models allows us to apply clustering to identify which patient are similar and different in terms of their coefficient. Those are like weight on the linear model. So for example, we found these two different clusters, and these two clusters have a different weight contributions of each feature. We also looked at this circadian, infradian, ultradian rhythm. And so these are some, these kind of interpretable, also multitask learning was helpful for understanding patient subtypes. So we are also doing relapse prediction models for this schizophrenia patient. And relapse events are very rare. So it is a super imbalanced data set. So what we want to do is we want to use this previous data set, smartphone prior data set, to predict whether the relapse event is happening in the future or not. And we also, for this study, we also computed this kind of template, behavioral rhythm template, to understand patient routine behaviors. And then we added these rhythm features to their self-reported EMA and demographics to predict relapse event. And then relapse event are much smaller. The size of the data is much smaller than other data set. So it is kind of also difficult to apply super sophisticated, complicated models. And so for personalization, we also have to think about another way to do it. Then in this case, we have tried kind of for finding a similar patient and in terms of their profiles, then try to use their features to optimize the models. and also for testing. And this kind of personalization is helpful. And we learned that this kind of rhythm features and also personalization are helpful, and also much better can give us much better performance than like randomly predicting relapse event. And we still have some other challenges. For example, we are collecting data from multimodal sensors, and so missing data modalities are very, very common. Then we could also apply some data imputation method, such as principal component analysis or autoencoder, but those methods might provide some bias. And also, we still have challenges in developing personalized model. And multitask learning and transfer learning, these are very computational heavy. And still, it shows a weak model adaptability to each individual. So this is one of our latest work. And so in this project, we are focusing on momentary stress detection instead of like daily or monthly. So these data are collected from multimodal physiological and behavioral sensors, like wrist and chest sensors that give us like skin conductance and heart rate. Then we have also momentary stress level self-reported assessment. Then the issue here is some sensors has much smaller data set. For example, some sensors can be sensitive to noise. And so in this case, we have much more number of sequences from ECG sensors than skin conductance. So if we want to combine these two sensors, then we might lose the data. So, but how can we leverage this kind of multimodal data? So that's the problem we are trying to solve. And so in this project, we decided to use the transformer model with self-attention network, because LSTM RNN seems to be very powerful, but also it requires a lot of computation and it takes time. So we decided to go with different models. Then in addition to that, since we need to kind of leverage the two different modalities of data. So we have three cases. We have one case when we have only skin conductance data. The second case, we have only ECG data. And third case is we have two modalities available. So we need to kind of design a better loss function to accommodate this kind of missing modality situation. And this work is still under reviews, but hopefully will be out very soon. But we found out this kind of modality fusion network framework will be very helpful to boost momentary stress detection performance. And in addition to that, we also wanted to personalize our model. So we decided to use this personalized attention framework. And so into this multi-fusion network. Then we found out if we use this personalized attention multi-fusion network, we can see the best performance, as well as we saw the reduced machine learning model size, which can be useful, friendly for mobile setting. So, so this is almost the last piece. So we are also currently running some intervention studies. So one of the intervention studies is for shift workers to help their sleep. And shift workers, so for example, doctors and medical doctors, medical doctors and nurses, even though they are living in the one time zone, they are working daytime, nighttime. They are shifting their work schedule, so they feel like they are jet lag, and their circadian rhythm is disrupted. And however, they need to go through the very important decisions in their work, then they won't be able to make errors. But a lot of them have sleep and health issues. So in this project, we are collecting Fitbit data from shift workers, and we are running our well-being prediction models on the server. And then in this system, we have also medical doctors. They review the data from shift workers, then also provide cognitive behavioral therapy suggestion to shift workers. So currently we are making also another models for like burnout risk prediction, also automatic suggestion selection. So this is still ongoing studies, but we are excited to have our models running and see the efficacy and effectiveness. And then we still have other challenges. So these are the other challenges we are currently working on. And so some of the challenges are, it is still harder to collect data, but especially like many labels, like mental health data relies a lot on self-report. And then compared to sensor data, which are coming in continuously, self-labels are much, much more expensive to obtain. So we need to kind of leverage unlabeled sensor data to improve our models. Then a lot of our models are very static. So we want to also make our models adaptive and changing over time. And we are also considering how can we design the better like AI human collaboration. So meaning machine learning patient collaboration or machine learning clinical staff collaboration. And lastly, but not at least, we also care about like user engagement and trust. So how can we improve, how can we get users engagement so that we can design a sustainable system. And also one of our ongoing work, we are also doing deep phenotyping work. This is also related to our, the first talk in the mental health session today. And so we are also doing like brain imaging, mobile sensing, some like blood, also some other behavioral sensing, as well as clinical assessment. So again, so we are aiming to design this kind of personalized feedback system to enhance people's health and well-being, also performance, by combining sensing inference intervention. And I'd like to thank my student and staff members. We have been working remotely since last year, but we started kind of going back to work in person little by little a few weeks ago. So we are excited to go back. And most of our work is a collaborative project. So I'd like to thank our collaborators in the different places in the States, in Europe, in Asia, also in academia and industry, as well as I'd like to thank the funding agencies allows us to do this kind of work. And also I'd like to thank everyone to listen to this talk, and I'll be very happy to take any questions. Thank you very much.
Thank you very much, Akane, for a nice talk. We already have our first question from Ojasvi. Ojasvi, you can now unmute yourself and ask your question.
Thank you, Megha. And thank you, Professor Sano. That was that's a very informative session on effective computing. I had a couple of questions. I'll start with one and probably wait for my chance on the next one. My first question was, when we look at certain affective disorders like schizophrenia, bipolar, and whatnot, they often get misconstrued or like misdiagnosed with certain disorders like ADHD or even what else? Autism and things like that, certain development disorders like these. There has been a fair amount of interest, say by Rosalind Pickard and groups at MIT Affective Media in pursuing the developmental disorders, in trying to understand them more. Was there a reason? And I was looking at the areas of concern that you approached in your study. Was there a reason you were focusing more on affective disorders rather than developmental?
Yeah, thank you very much for your question. Oh, am I mute? I think I'm fine. Yeah, I was also working. I have also experience in working on like behavioral, like autism and other disorders as well. I was also actually in Rosa's group. I did my PhD with her, and at some point I was also developing some tools for people with autism. But recently, my interest is more like moving to mental health disorders. But I believe that this kind of tools can be definitely applied to developmental disorders as well.
Right, right. Do you? Okay, I'll ask the rest of my questions later. Thank you.
Thank you very much.
So Nagaranjan, you can go ahead now, or you can unmute yourself.
Yeah.
I hope would
yeah. You can hear me. Thank you, Megha, and thank you, Professor Sano, for a very detailed and very huge work on mental well-being. Yeah, my question is pretty complex, and already you have mentioned in your challenge. It's about the labelings. Most of the databases and most of the data we acquire or the databases exist over the research zone, they all are being mostly labeled using self ratings. Yeah, and you believe, or in general, we have to believe that what is being reported by the subject is pretty correct, and we have to go with that self rating. It's like if the subject is not feeling happy, but he can mention it like he's neutral. Yeah. So how do you have any suggestion on such challenge, like how you can motivate a subject to provide you the exact self-rating, or is there any other way by which we can get a better annotations on the data? Because when you talk about data for 1 year and then you end up with saying the subject just mentioned one rating, and then your whole huge data is dependent on one annotation, which is really a complex thing. Yeah. Maybe an eye on and suggestions on that.
Yeah, so thank you for your question. Yeah, probably my answer might not be the best because I'm just engineer, so probably I should also ask the same question to the clinical people. But that's true. So that is the one of our biggest challenges. And so for some studies we have self-report assessment as well as the clinical assessment. So psychiatrist make some assessment, and based on criteria, or also we also use some standardized questionnaires. But that's true. So self-report might not be reliable. So that's also another thing. Maybe we can also dig into, with like uncertainty from self-report, how can we develop more like robust or reliable models? So actually, we haven't started that modeling yet, but that's something we are interested in. And for another maybe answer, instead of relying on self-report, we could also rely on something objectively measurable. So that means we can measure some behaviors, also some physiological like autonomous responses, and then kind of reduce relying on self-report. But I'm not sure. I might not be answering your question fully. But do you have any ideas about it?
Yeah, I'm also working on something similar to it. Like though when I started my work on the self-reporting part, I always end up with like, how can you make someone to be motivated and tell me the real
Oh yeah,
emotion?
motivation
What?
part.
Yeah.
Yes.
So
Yeah, I think also yeah, like rather than randomly sampling, like asking them to self-report, maybe we could also identify the best timing to ask. So this is also related to the previous talk. But because if people are busy and doing something else, and that might not be a good timing, then so I mean, our sensor measurement can be also used to understand patient or participant context.
Yeah,
Then
exactly.
that might be one way to go.
Yeah, exactly. That's the point was I was just highlighting, like I was more interested on the instrumentational part of defining these annotations. Probably I'm working on it, and soon that the work is also under preparation, and soon will get out and get published, and that could be an initial benchmark for this critical challenge of self annotations. Let's see. Okay, perfect. Thank you so much for the talk.
Thank you very much.
Okay. Sonam, you can go ahead now. Sonam, do you have a question? Okay, I think till he tries to unmute himself, Niloy, you can go ahead.
Hello, hi. This was a great talk. So I just have some curiosity. How good is this sleep calculation? You have done a lot.
Yes. So for different studies, we use different devices. And for the study, I introduced like sleep regularity data. We use actigraphy, like clinically validated actigraphy, and also sleep diary. So we combine those two assessments to get more accurate sleep data. Then, of course, if we could do polysomnography PSG, that would be better. But since our data is long term, so we won't be able to. We wouldn't have been able to do it.
So I have a simple thing that, like, for example, whenever I get up in the night, I see my mobile phone. So somehow my mobile phone knows when I am awake. So can that signal be used?
I think so. Yes. Today I didn't introduce that work, but we also develop machine learning classifier to recognize like sleep onset and offset from smartphone data and also wearable data, and it has pretty good performance.
Sure.
Hello, Professor. Hello, Professor Sano. Thank you for the wonderful explanation about the project, work. Regarding the noise detection techniques, are you applying statistical methods for identifying noise, or you have any domain specific techniques?
Sorry.
Identifying noise. Identifying and correcting noise in the data set, are you applying any statistical based approaches or any domain specific approaches are used?
I see. To understanding noise, maybe if you could tell me more about share me more about what you mean, I think that'll be helpful. Sorry.
No, can you tell us the noise identification approaches you use?
I see. So for some signals, we use some digital filtering to remove noise, and so that is based on some prior domain knowledge that we should look at this specific frequency domain, for example.
Okay.
Or and then for some signals, we could also define, outliers based on the distribution, or for some signals, we could also identify the specific shapes, morphological information of the noise with visual inspection. So when we made a skin conductance noise detection model, actually we use both approach. So we use both visual inspection and also some data-driven method.
Okay. Thank you, Professor.
Thank you very much.
Sneha Santoshi, you can go ahead with your question now. You can unmute yourself and go ahead with your question.
Thank you, Dr. Akane. It was indeed a very good presentation, very thoughtful and insightful. I just wanted to ask that, is there any scope of adding clinical data to your analysis?
Yes.
The data which comes from the doctor directly. And second part of my question is that as already been discussed about the motivation for the user to give the data, correct data, is there any way how to detect, because you don't know whether the data is reliable or not, anything about the reliability of the data which you are getting directly from the patient? He or she may not be telling you the truth. So how do we handle that?
Mm-hmm. So first part is engagement. Yes, so we are very interested in understanding engagement. So not only about response, whether they respond to this surveys, but also whether they are engaging in answering, also being in the study or using the app, etc. too. And then how that affect the outcome variables. Also, how can we measure that engagement? And that's still ongoing work. Then reliability, yes, that's true. So if the participant are telling something not true, then that would be a problem. But we might be able to kind of understand some kind of contradiction within our data. For example, sometimes we might see some contradictory results if we look at some sensor data versus self-report. So then if we see something, maybe we doubt this might be unreliable, we might be able to ask patient or participant back to redefine their condition. Am I answering your question?
Yes, absolutely. Thank you. Because this problem we have in clinical data also, whenever we are talking about clinical data, we have models of clinical data, and there also we have a problem of data reliability.
Yeah, so yeah, I have so for today's talk, I didn't talk about the including clinical data. Some of the data the clinician assessment, but I'd love to also include some clinical data if there is any possibility. So I'd love to collaborate with some of you if you are working on something like that.
Because that will help. That will, in fact, help you to assess whether the data which the patient is directly giving is reliable enough or not. Because if we club the data, that may help you analyze things better.
Thank you so much. I hate, but we have to move to the next question.
Thank you so much. Thank you.
Thank you.
Marty Kruger, you can go ahead with your question.
Yes, this is Matti Kruger speaking from Honda Research Institute. So thank you very much for your very interesting and impressive talk. So I hope nobody has asked this question yet because I briefly dropped out of the discussion. But I'm very much interested in the self-attention network for modality fusion. And I'm wondering whether this comes with some trade-off compared to the LSTM approach you talked about, because there might be less redundancy available in the data when the attention is focused on specific sensors. So do you know if, so I'm not sure whether my understanding is correct, but would this make it more susceptible to noise than the LSTM approach, basically? Or is this not the case?
Good point. Yeah, I mean, that's very good point. We haven't analyzed that aspect yet. So probably that would be our next step, and we'd love to kind of evaluate how our model respond to noise compared to LSTM.
Okay, thank you for your question. Answer. Then I'll keep an eye on your publications.
Thank you very much.
Radek, Hussein, you can go next.
Thank you for your nice presentation. I'm Sadiq from Magdeburg University. What I'm interested is the interestingness of the generated pattern. How we can say that the generated result is interesting or not? What is the criteria that you use it to say this pattern that how you get it is interesting or not? I mean, this is just what I'm caring about.
Yeah, so I think you are talking about so sometimes, yeah, our results, for example, we try to interpret what kind of features are learned in auto encoder model, and sometimes it is difficult to interpret. Then sometimes it's we might not be able to understand it, unfortunately. Then that that finding might be interesting because something probably we haven't found. Or so kind of interesting or not is maybe something subjective, but did you find some, like, I don't know, interesting like features or biomarkers in your model or in your research? Or
Yeah, just when I see the symptoms predictions, when you just generated these symptoms, so we can see the symptoms is interesting because they lead to some knowledge. Whereas some other, they are well known or they are just a noise or something. So how we can measure these symptoms really interesting for us or not?
That's true. Yeah, very good point. Yeah, whether the something we found is just like noise or something really interesting. I think we need to see the reproducibility, or whether that is like how likely that is happening in a different sets of data set.
Yeah, it is. There is some criteria like belief network or something. I don't know. This is what I'm really interested in. I'm studying it. I want to find out. Thank you very much.
Thank you very much.
Sonam, you can go ahead. One last question.
Yeah, hi. Thank you for a wonderful talk. And the model is, the statistical model, the statistical part is really great, and I really loved it. So from the perspective of a third world country, or like the countries which are not that developed, there is a gap between the collecting information digitally. So is there any way in which the data can be collected from people who do not have a digital device? Probably having an IoT device can be a solution according to my understanding. And also the second problem is about the data privacy. So have you taken care of that? Because that is an issue which really bothers people.
Yes, those are great questions. Yes, so yeah, as you said, probably IoT devices could be another. So today I mostly talked about mobile, like wearable devices, but we could also put some devices in our house, on a bed, or then that. So yeah, currently I think we are more increasing number of IoT devices, right? Then another thing is if we have like increased number of the kind of device, then the privacy issue is also another concern. And yes, so Yeah, I totally agree. So we are kind of thinking about, which part of our models should be, the processing or models should be run locally, or which part of the data should go, where, which place. And then it is kind of very difficult to, aggregate this multimodal data. Then, I mean, for maybe prototype purpose, it might be just good with just go with smartphone data. Then, because if we try to aggregate so many different modalities, it add more complexity and also privacy issues. So we are interested in, of course, and also we care about the privacy and of the data from users. But I might not have the exact answer to solve that for now.
Sure. I mean, these are all open-ended questions. So thank you so much. Great talk.
Thank you very much. A great talk. Thank you, Akane, and wonderful discussion. Thanks, everybody.
Thank you very much.